Good afternoon, guys. Thanks for coming to the student seminar series on quantum advances. Tonight we have a speaker from Professor John Hu's lab. He's a PhD student in the Department of Physics and Astronomy, Christian. And I will just hand it to you, and we really look forward to our talk tonight. Thank you.
Thanks. All right, so my name is Christian Lang, and today I'm going to be talking about organic dye molecules and their use in coherent light matter interactions. So we've had a lot of talk about quantum mechanics, so I'm not going to go too much into the motivation for quantum mechanics at this point. But I will just say one thing about quantum mechanics which differentiates it from other fields of science, right? Because in general, what we're trying to do with science, and especially with technology, is we're trying to take systems that we understand and kind of put borders around them, right? Let's say you work in thermodynamics, you're trying to make an engine, right? You want to control where the heat is, right? It's localized in the piston and it's not anywhere else, right? You're not losing that energy anywhere else, right? Well, let's say you work in semiconductors and you want to make a chip, right? You want the electrons to go this far and no farther until you say so. Then you release the gate and they go, right? So all the science and technology is about setting borders and gates and being able to control where physical objects move, right? But with quantum mechanics, the story is a little bit different, right? Because you say, okay, I want to put a border around a quantum mechanical state, right? But it's not so obvious how to do that because a quantum mechanical state doesn't exist in one place, right? It's a mode which is defined over all of space, from r equals 0 to r equals infinity over all 4 pi radians. It exists everywhere, right? And so it's not clear how to put a border around the scene to keep it right where you want it, right? And so the way we define things in terms of quantum mechanics is with orthogonality, right? It's like, okay, you have this state and the rest of the universe, and you can't separate it spatially from the rest of the universe, but maybe you can help to make it orthogonal to the rest of the universe, right? So that it's like perpendicular. Here's the rest of the universe, and here's your state, and they never mess with each other. They never couple with each other. So that's the goal of quantum information, so that you can control the flow of quantum states without them being lost to their environment by making them orthogonal, right? So there are necessarily infinitely many ways that you can transfer quantum information if you want to make a quantum computer or a quantum network. But we want one which is weakly coupled to the rest of the universe, right? That's the idea. We want a quantum system which is isolated from the rest of the universe, right? And one natural way to do that is with a photon, right? Because light, miraculously, and this just came out of the mathematics, when the cosmic microwave background was being formed, and you had the splitting between the W boson and the photon. Is it W boson? Z boson, whatever, it doesn't matter. Is that you somehow ended up with a boson which does not interact very strongly with anything at all. It just passes through most things. For an example, if you have 1550 nanometer light, right, 1.5 micron long light, and you put it into a fiber optic cable, it will travel a kilometer before it loses even 3%. Right. So if you have like a high purity dielectric like silica or a silicon nitride, light interacts very weakly with it. It passes right through. And this is exactly what we need for something which can carry quantum information. You couple that with the fact that light has many ways it can store quantum information. It has polarization. You can have a superposition of polarization. You can have a superposition of phase. You can have a superposition of spin, because light actually has spin also. You can even have a superposition of spatial modes, right? 2 photons entangled in 2 different places, right? So many different ways you can carry quantum information, along with the bonus fact that it doesn't interact with most of the environment, along with the fact that photons don't interact with each other at all, which is also quite a miracle I might add, because most of the time in physics, we're approximating things as harmonic oscillators, but with a photon, when you write out the Hamiltonian, it's already a harmonic oscillator. You don't need to approximate it, right? Maxwell's equations are a harmonic oscillator, and a harmonic oscillator is evenly spaced energy levels that don't interact with each other, right? And so this is all perfectly and conveniently packaged in a photon. So it's, in theory, a great way to carry quantum information, right? And so the fundamental building block of a quantum network or a quantum system based upon a photon is what's called a single photon source, right? Because, okay, well, light is convenient in many ways, but one of the inconveniences is that there are infinitely many modes of light that you could couple to. And the idea is that you want to have a quantum state, which has quantum information in it, which couples to a single mode of light and no others, right? Because it's only if you can couple to a single mode of light that you can be orthogonal to the rest of the universe, so that you're not dephasing, you're not losing information to the rest of the universe. And so you want a whole quantum system where you have quantum states that carry information, coupled strongly with a single mode of light, couples to other quantum systems, and then you can do computations, right? And so the idea of a single photon emitter is a quantum state which couples to a single mode of light, right? Okay, and that's called indistinguishability, right? And so there are three main figures of merit for single photon emitter. They are the indistinguishability, the purity of the photon emitter, and the efficiency. The photon purity essentially means how likely are you to get two photons at the same time from this emitter, right? Because you know it's one state, right? The electron is excited. The second state decays down, releases a photon. If you get two photons at the same time, well, it couldn't have come from this state, so it must have come from something else in the system. So it means you have an impure system, a system which is releasing light, which isn't the light that you think it is. So for most quantum applications, we need the photon purity to be less than 1%, or ideally less than 0.1%, right? Now the efficiency, that's just a measure of how reliable is this thing, right? So if you, let's see the quantum system, you probe it with a photon, how likely is it that you'll excite it? And then how likely is it that that'll decay in the way that you want it to decay? And then how likely is it that you'll be able to measure the photon that's released, right? And all those, you multiply those together, and that gives you the quantum efficiency, right? And for like very baseline quantum key distribution, you want the quantum efficiency to be at least 50%. But ideally, for any like linear optical quantum computation, you need 99% or more, 99.9%, right? And the indistinguishability, that's just saying that every photon which the system releases should be the exact same mode, polarization, everything. And the way you measure that is actually quite interesting. You take a beam splitter and send two photons, which you think are identical, into the beam splitter. And if they are truly identical, something very strange happens. Out of the other side of the beam splitter come two photons together, either up together or down together, but never separate, right? It's a very strange phenomenon, right? If you put two bosons into a beam splitter, they will group together if and only if they're identical. And the degree to which they group together tells you how identical they are. I don't have time to go into the intuition of this app like right now, but if you guys ask that question when we're done, maybe I can try to give intuitive explanation for why it is that bosons tend to group together. So those are three figures of merit that we're dealing with. So the first quantum state, which was demonstrated to be a single photon source, is that of the atom. And the atom is ideal in many respects, right? You have, well, first of all, every atom, if it's the same isotope, is identical to every other atom, right? If you have cesium, all the cesium transitions are identical between systems, right? And so if each one is a node, they can all talk to each other, and they're talking with the same photon mode, right? And that's convenient. And an atom doesn't change over time. And so it's always like the exact same mode. And within an atom, all the states are orthogonal, right? So you don't have any kind of dephasing. You just have a very simple, like two-level state. You're here, and then you're back home, always releasing identical photons. And so for a while, these were considered, and these still are in many respects, the ideal quantum emitters. But the problem is, well, let's say you actually use an atom to generate single photons. Well, now you want to make a network. Well, you have to use a second atom to generate single photons, right? And that's difficult because to get single photons from an atom, you need magneto-optical trap, you need tweezers, and then you need high NA objectives. Realistically speaking, you'll need some kind of cavity to enhance the decay, so it decays in the way that you want to decouple it. And then after you add all that things, you get to build it all again just to have two nodes in your quantum network, right? And so the scalability is just really, really difficult. Now, if you're talking about like just dipole transitions, you have a bunch of atoms and they're just interacting dipole, that's fine. You can just make a whole array of those in one chamber, right? But if you're talking about you want an atom to release a photon, which interacts with another atom, you're talking a brand new $500,000 vacuum chamber and optical setup for every node in the network. It's just not scalable at all. And so we need to move to the solid state. And so, well, first of all, it's an open question. Is it even possible to make a reliable source of indistinguishable photons in the solid state, right? Because indistinguishable means, but it implies that whatever generates the photons is also indistinguishable. But we know that can't be true in the macroscopic world, right? If you have two crystals that release photons and they're big enough to see with your eyes, there's no way they're identical, not perfectly. There's always going to be some difference between the two. And so you could be skeptical whether it's even possible at all to generate single photons. And more than that, they're not. I mean, the beauty of an atom is that you can make it orthogonal to the universe by putting it in a vacuum chamber, right? Because then it's separate spatially from the rest of the universe. But if it's solid state, whatever is emitting photons is embedded inside of all this other junk and is coupling with all this other junk, right? and this other junk we call phonon. So phonon is like a lattice vibration. And so if you have this, let's say a molecule, which emits light, which is what I'm going to talk about today, which you have phonons, those are squeezing and stretching that molecule. And every time you squeeze or stretch it, you're changing you're changing the energy spacing, which means you're changing what frequency of photon it will release, right? And so whenever you have phonons, there's no way you can create the same photon twice from the emitter because it's being jostled all around. But miraculously, it's been demonstrated that with some quantum emitters, if you cool them down to 4 Kelvin, you can actually freeze out these phonon sidebands. You can actually make it so phonons do not exist in your system, essentially. And that the emitter acts as if it's floating in free space. It acts as if it would be. Like even though it's in this crystal, if the crystal is cold enough, it gives you the same thing as if it were just floating in a vacuum chamber, right? And so from color centers and diamonds, particularly nitrogen vacant centers, and with gallium arsenide quantum dots, they've demonstrated what's called transform limited lifetimes. What does that mean? Well, it means that the frequency of light, which is released, is the exact same frequency of light you would expect if there were nothing else. If there were no crystal, no phonons messing with it. And you can actually achieve that even in a crystal as long as you cool it cold enough. So this is already quite remarkable. Now, unfortunately, there are some problems with NV centers and diamonds and with ectaxial quantum dots. The problem with NV centers and diamond is that, well, you have this two-state transition, but you have all these other things that can decay to. And in reality, it only decays from the purely electronic transition about 3% of the time, right? So it does emit indistinguishable photons, but only like 3% of the time. So it's not ideal, especially because, we saw for a real application, you need realistic something like 99%. Gallium arsenide quantum dots are also promising, but the interesting thing about those is that the frequency of light that they generate, because they're essentially a quantum well created, is a quantum dot, and the size of it changes what frequency of light you generate. And since these are man-made things, every quantum dot is a different size, which means every quantum dot releases a different frequency of light, and the frequency that a single quantum dot emits changes over time. And so even though they can be indistinguishable, like 2 in a row, over time, it's really not indistinguishable. And, quantum dot to quantum dot are really not distinguishable. So, there's more improvement that can be made. Now, we've seen that when you move from an atom to a solid state system, all those beautiful quantum properties went downwards, right? As you increase the complexity of the system, the purity of the quantum system decreased. And so you'd expect that if you move to something that's way more complicated, let's say if you move from an NV center, which is just 2 things, by the way, it's a nitrogen and it's a nothing, a vacancy inside of a diamond. If you move from that to something way more complicated, like a whole organic molecule, you'd expect that it would get way worse. But miraculously, once again, it was demonstrated in the 90s by Michel Lerit that an organic molecule inside an organic matrix at liquid helium temperatures can demonstrate a lifetime limited transition. Once again, that means that you can, when you cool it down enough, the dimethyl molecule in this case is it's strongly enough connected to the lattice that it doesn't move, right? It's not jumping all over the place, but it's loosely enough connected that you can actually decouple it from all the phonons jostling it around. And then it acts as if it's just a molecule floating inside some vacuum chamber. And you can actually achieve that, which is quite remarkable. But then dimethyl also has a bunch of other properties which other quantum emitters don't. For example, because it's literally something you can just dope into a crystal, you can dope more of it. In fact, you can put as many of these molecules into a crystal as you want for whatever purpose you want, right? Like you don't have this with NV centers. Like NV centers, it's rather hard to create this nitrogen vacancy pair, and it's kind of stochastic. And so if you want to make a tiny one that you can like couple to a nanophotonic crystal cavity, there's no guarantee at all that it'll have the transition that you want. But with a organic molecule in a crystal, you can make the crystal and you can dope it with as much as you like. In addition, you have, because you can synthesize these things, you have complete control over how large they are. It's not like, making a larger diamond, which is much harder. It's like, just add more anthracene. And, we've been able to demonstrate in our lab crystals that are about 100 microns or less than 100 microns wide, not in this picture, to crystals that are a millimeter wide, right? That's 4 orders of magnitude. You have huge control over the morphology of these things. But most importantly, as compared to NV centers, for some reason, this is 58 atoms in the dimethyl molecule. This thing is huge. Yet somehow the electronic states are well defined enough that it decays from the state you want 50% of the time, right? You compare that, it's not 99%, right? This thing isn't, it's not an atom, it's not 100%, but it's not 3% either, like the nitrogen vacancy center. So even though you increase the complexity of your system, somehow it's better in terms of releasing single photons often, right? 50% of the time. And then finally, because this is, once we realize, okay, you increase the complexity of your system doesn't necessarily decrease its quantum properties, like when you move to an organic matrix, something that opens up a whole world, right? There are a lot of organic molecules, which means there are a lot of different combinations of organic molecules inside crystals that you can try for different applications, If you can make a molecule that emitted at 1550 nanometers of light, and then couple that to a fiber and go a kilometer and only lose 2% of it, that'd be fantastic. So even though this is already phenomenal and we only discovered these in the 90s, there's a lot of room for improvement. And so just to give you an idea of how you can make one of these, there are two ways in our lab we make them. One's called the so-called reprecipitation protocol, and the other one's co-sublimation. So with reprecipitation, you essentially take a solution of anthracene and dibenzotoluene molecules, all floating in acetone, and you take some of this and you put it in water while it's sonicating. And so you have this little bubble, this micro bubble of acetone with anthracene and DBT, and acetone dissolves into the water until there's no acetone left and all the anthracene and DBT come together and form a crystal, right? And well, it's quite remarkable because even if you do like this, it's quite easy to do. You just like take it and you just inject it into the water. It's high enough purity that, as you can see from this is a line scan of a bunch of molecules in the crystal. And then, so the orange is just a regular line scan. And then you twisted the polarization of the light 40 degrees, and then you do another line scan, and that's a blue line scan. And what you see is all the molecules decrease when you move the polarization a little bit. What does that mean? Well, it means that even with this relatively easy synthesis protocol, all the molecules are oriented exactly in the same direction. Their dipole moments are all in the exact same direction, which is, very high purity considering how easy it was to make them. Honestly, it only takes a couple of hours. And then the other way we can make them is with this co-sublimation chamber. And this is the benefit. So what you do is you have two crucibles, anthracene, dibenzotoluene, and you can control the temperature of the crucibles, you can control the pressure of the nitrogen atmosphere, you can control the temperature of a tough substrate, and essentially it evaporates the molecules, and then they condense and precipitate on the top, and then you can have a crystal, right? And the benefit of this is that because you can control the temperatures, you're essentially purifying the crystal while you're making it. As you can make very pure, very large, like millimeter large crystals with like absolute purity, very narrow line widths. And that's something also that we've been able to work on. Okay, so I've been bragging a lot about organic molecules, but as I mentioned at the beginning, if you want to use it for anything useful, you need an efficiency of greater than 99%. So 50% is just not good enough. You need to enhance it somehow. And one way to enhance the quantum emission of an emitter is to put it inside a photonic cavity, right? So a photonic cavity, it essentially works by, like if you took two mirrors and you put a molecule or an emitter in between those two mirrors, and then you put a photon in between the two mirrors, right? Because the photon is not going to interact with it very much. There's not strong coupling. But if it bounces back and forth enough times, it sees the atom many, many times, and eventually maybe it'll get absorbed. And so the trick with the photonic cavity is, okay, well, you don't have very strong coupling between light and matter. We'll just leave it for a long time, right? Like let it interact many times, and eventually it'll couple. So that's the intuition behind the cavity. It's essentially two mirrors. And then the equation which explains how much of your light is emitted into the cavity mode versus would be emitted just into free space otherwise is called the Purcell factor. And the Purcell factor, there are a number of ways to intuitively understand it, but the best way to represent it is essentially the size of the photon, size in quotation marks, the size of the photon that it would release into free space, divided by the size of the photon in the cavity, multiplied by the lifetime of the photon in the cavity, right? And so you have a very strong, like a very high energy density, very compact cavity, and then light lasts a long time in between. They're more likely to strongly couple with the emitter, right? And just as a side note, like I wouldn't have expected this if it was up to me to come up with this, right? Because I would have expected, okay, you want to really get all the photons that this thing releases, well, then you want to mode match with it. And so you want a cavity mode which looks exactly like a dipole mode. coming from the atom, but that isn't the case at all. You actually want the cavity mode to be way smaller, way different in shape than the atom mode, and it's that which enhances the emission. So it's kind of non-intuitive, but it's really remarkable that it works.
How can you simulate the free space mode by a cavity? Like it has to be an approximation, right?
Oh no, so the free space mode is just a dipole mode, right? It's quite simple. Like every two-state system is just going to be a dipole, right? And then the cavity mode, just the bare cavity mode, you can calculate that as, finite difference time domain software. You just forget about the atom, just say two mirrors. What's the mode between there? And you can actually solve that using three-dimensional software. And then the ratio between those is the Purcell factor.
But you want it to be the free space mode, right? You want it to be the dipole mode, and in the end, right?
Oh, no, sorry. I should think. I was saying that's what I would have expected. I would have expected that you want the cavity mode to look like the dipole mode so that there's strong mode matching. But in reality, you get strong coupling when the cavity mode is way smaller than the dipole mode, right? So it's not non-intuitive at all. But okay, so you made a cavity and you enhance the amount of light of indistinguishable photons that this emitter releases. But the hard thing to play with nanophotonics is that you want to maximize the lifetime of the photon in the cavity so that it emits more of the atom. But then you also need it to leave the cavity eventually, right? And leave the cavity in the way that you want. Because you can imagine if it's staying there for too long, eventually it's going to hit a defect and just ping, and then it's gone. And you can never touch it again, right? And so there's kind of this trade-off between how long does the photon live, but you also want it to leave in the way you want. And so just looking at this problem, it's not at all obvious that you have a cavity, the same wavelength which maximizes the energy density in the cavity, right? Which maximizes the coupling of the emitter to the cavity. You're not sure that's the same wavelength which is going to eventually couple out of the cavity and that you can actually do something with it, right? But as it turns out, they are the same wavelengths. And so you can kind of understand it this way. So you have two mirrors, right? And then there's some light coming from the left side, and this is some amplitude, right? So because it's a mirror, the light's going to come in and it's going to decay exponentially into the cavity. And so there's just a little bit of energy in the cavity, right? And then all the energy in the cavity, that's going to decay exponentially outside, right? But for energy conservation, the amount of energy that comes in must equal the energy that comes out. So what's going to happen is the energy in the cavity will build, will keep dumping energy in there until it's so high that the energy that's leaving it is equal to the energy coming in, right? And so that's a way of understanding that when you're on resonance, the energy density is maximized and transmission is unity. 100% transmission and the highest energy density, both at the same time. As you maximize the coupling to the atom to the cavity and maximize the coupling of the cavity to your waveguide. So it's pretty cool how that works out. Now, of course, in reality, like I said, there are defects. And so you need to balance how good your cavity is versus how easy it is to couple out so that you don't, because if it stays there forever in a world of defects, you're going to scatter out of the cavity and then you're going to lose the photon you worked so hard for. So, okay, I'm going to beat this point one more time because it is really kind of special, right? It's like, okay, so you have an emitter and in free space, it releases a dipole mode, right? And that dipole mode, only a little bit of that would couple to a waveguide. And yet somehow, when you put it inside a cavity, you can enhance that amount. You can make it so most of the light goes into the waveguide, right? But then it's like, how does this make any sense? I mean, it's the same dipole, right? A dipole releases a dipole emission spectrum, right? You're not changing the atom, you're just putting it inside this waveguide, right? And so it's not really intuitive to understand how, because it's acting like it's changing the emission that comes out of the emitter, right? It's acting like putting it into the cavity makes it so whenever you excite it and then it comes down, it emits a shape which fits perfectly the waveguide. And it makes no sense because it's still just a dipole, right? And so that's why whenever you're doing, cavity and nanophotonics, you have to understand that you can't treat the atom or the emitter separate from the cavity. That's what it means for them to be coupled. They're no longer two entities, they're one entity, they're married together, right? It's not that you have an emitter in the cavity, it's that the whole cavity atom conjugate is an emitter. And that whole emitter, which you've engineered, emits waveguide photons, right, with high purity. That's what's going on here. So it's like your emitter is two balls which are connected by a spring, it's oscillating. And then when you put it in a cavity, you have another spring connected to something else, right? Like the whole thing is coupled together. You can't, say, you can't separate it and say, but this just is a dipole emitter. You know, it's not a dipole emitter. The whole thing is the emitter. So, okay, just had to nail down that point. And then the fact that there is a coupled system means that it actually changes the energy levels, right? So if you have two springs and three masses, you know that there are two eigenmodes. There's a symmetric one and an anti-symmetric one. Similarly, when you put an emitter, a two-state emitter, into a cavity, you end up with three states. The whole thing is an emitter, and now it has three states. And so you end up with this thing where here's this blue line, that's the emitter transition. And if you put it into a cavity, that second line splits into two, right? A positive and negative one. One where it's symmetric with the cavity, and the other one where it's like anti-symmetric with the cavity, right? And then this is something you can really do something with, right? So for example, you could say, you can send in two photons, which are resonant to the emitter, right? And it'll absorb one of them and then emit it outside the other side. But it can't absorb two because you've broken the frequency. It's no longer a harmonic oscillator, right? Harmonic oscillator is every energy level evenly spaced. But now it is no longer like that. And so you can make a filter so it only lets one photon pass at a time, or only two photons pass at a time, right? So you can see now you have a nonlinear element. Now you can start to make some really cool photonic circuits. And once again, I don't have enough time to talk about this, but if anyone wants to ask me how to make like a Dwan-Kimball gate, which is the C naught gate, which you could create a quantum computer out of, I can explain it afterwards if anyone asks that question. But it's the fact that an emitter is not distinguishable from cavity, which allows us to use the cavity for photonic circuits. Okay, this is a picture of our prototype of cavity, just to give you an idea of what the whole thing looks like. So grating couplers either end, they'll send in a laser, and these grating, it's like a diffraction grating. You send a laser in and it sends out at a different angle. Only it's optimized, so you send the laser, it sends the laser straight into the waveguide, right? That's what those do. And then these holes, right, light reflects off of each hole, and all the reflections interfere in such a way that you essentially have a mirror. It acts like a mirror. Mirror here, a mirror here, and then in the middle, you get tiny holes. And what those tiny holes do is they change the effective index of refraction of the material, so the light passes very slowly. It's just kind of a trick to do, right? So you have a mirror, and then in between, the light moves very slowly, right? And so not only are you bouncing back and forth, you're also moving slowly. And so when you put an emitter near, it takes a long time to interact with the emitter, and you very greatly enhanced emitter matter coupling, right? And so the dream eventually is to take a nanocrystal, a dibenzotyrrolene, which we've been able to make and been able to show that you have lifetime limited transitions, and to put that as close as possible to that maximal energy density in the center of the cavity. Ideally, you'd be able to put it into one of the holes, because that's where it's the strongest. But even if we can just get it evanescently coupled, it'll still be good. We'll still be able to get some strong enhancement of the light that is released from the atom. And then quickly before I move on, I just want to mention how cool it is that like you can make these 2D photonic structures, which are like, if you can make the right interference pattern, you can do anything, right? Because you think about the graded couplers, those are acting like a mirror to bend the light and a lens to focus the light to fiber couple at the same time, right? And it's just this 2D pattern. So it's something to think about, right? Everything is interference. Okay. So how do you actually get a nanocrystal DDT coupled to an antiphonic crystal waveguide? A lot of different ways to nano manipulate things, and most of them are super, super difficult, right? It's one way to do it. This is what's done with NV sensors and nanodiamonds, is to take an AFM probe, probing around, see, oh, there's a nanodiamond over here, and you just bring it down, and then just try to pick it up, right? Just try to use those very close forces to pick up the nanodiamond, and then you can tell that you picked it up because you don't see anything anymore. Bring it over your cavity and just like try to release it, right? So it's a very stochastic process, kind of difficult. That might be something you might have to do in the future. But what we found, because you can make these things in solution, like I mentioned, you just take nanocrystals in water and you just drop past them onto a bunch of holes. That's what these are, either bullseyes or the hole in the middle. What happens is that they tend to clump around the holes, just naturally. Why is that? So it's like, we don't know, first of all, but you can imagine if you have a hole, there's water in it. Well, the ratio of surface area exposed to volume is very low compared to all the rest of the water. So the rest of the water is going to evaporate first, and then you're going to be left with this hole with a little bit of water in there. And maybe in that process, things are just getting sucked near the hole because the hole is the last thing to dry out, right? And because water is sticky, the nanocrystals are just just reaching for that last drop of water, and then it dries out, and then you end up with these phenomena where they just kind of tend to clump around the holes. So we're based on that picture, the fluorescence image at the top, you can zoom in, and it really, really looks like there's fluorescence coming from the center of the hole. But we won't know for absolute sure if you have a nanocrystal in the hole until we like put the hole near a photonic crystal waveguide and actually see coupling out the gradient couplers. So that's the next step, like prove that using this stochastic process, we're able to position, molecules within a micron of a structure with absolute ease compared to everyone else. That'd make everyone else really jealous, I think. But okay, so I've gone through all this, and ideally you can take a very good quantum emitter like dibenzotyrrolene, and then even though it starts out really good, you can enhance that by putting it in a photonic crystal cavity so that it preferentially decays into the way that you want it to decay. But now you still need to have this, if you want to make a circuit, you still need to have talking between these molecules, right? And the problem with anything that's solid state, dibenzotyrrolene included, is there's inhomogeneous broadening. That means even if the peaks are narrow, they're all different from each other, right? Any kind of strain, imperfection, location of the molecule is going to move the resonant frequency. And if you want to remember, like what we're trying to do when we're making a quantum system, everything needs to be mode matched. And so you need all your molecules in the system to have exactly the same frequency. So how do you achieve that? The number of different ways to change the frequency of a two-state system. There's Stark shifting. That's where you apply an electric field. You can do that by like putting down metal very near to your, like a nanopattern metal very near to your emitter, and then putting a bias voltage there. And the electric field gradient will actually stretch that molecule and then make it emit in a different wavelength. You can use that to kind of tune the wavelength to be what you want. You can do something similar with magnetic fields. This is an example that was done with very large, like 100 micron large quantum dots. But it's actually also been demonstrated with our system, and not that we did. Alex Clark from the UK did it. But you can use strain, like you can bend your crystal by using the piezo, and that strain will also tune the emission frequency. But we might not have to do this because dibenzotyrrolene has another trick up its sleeve, and that's the fact that if you shine intense enough laser light onto dibenzotyrrolene molecule, it will shift the resonant frequency, and it will stay shifted after you turn the laser light off for hours to days. This is very strange, right? Like, not really something we see in other quantum emitters. For some reason, if you shine an intense laser light, it's not fully understood, you'll bend the frequency and you turn the laser light and it stays bent for a long period of time. And Costanza Toninelli actually demonstrated, so the inhomogeneous broadening is something like a terahertz, or maybe 100 gigahertz or something like that. But she was able to take resonances which are separated by 20 gigahertz and bring them within two line widths of each other. Bring them all over together to overlap, right? Just using light, and it stayed moved. It stayed shifted, which is quite interesting. The way they postulated this happens is that the dibenzotyrrolene molecule and the anthracene matrix that it's embedded in, if you excite it hard enough, maybe you can get an electron to jump out of the dibenzotyrrolene molecule into the surrounding matrix, right? And so you have an electron in an anthracene molecule next to this. And then maybe this will absorb an electron from somewhere else, and then boom, electric field, positive field over here, negative, positive, and then you have electric field gradient. And if you do this enough, you're constantly like shooting electrons out there. You can build like a charged matrix that will cause a circuit. You don't really know if that's the case for sure. That's the first proposal which has been used to explain very, very strange behavior, but it's very promising that we're able to get line widths to overlap from 20 gigahertz away. This is really, really something special. So, okay, and then once we're moving on now, because like once you're able to take two quantum emitters in separate places in space and align their frequencies. Now, of course, you could do some of the quantum circuits I could describe. You could, potentially go in the direction of quantum computing, although more realistically, you could do something like boson sampling. But then, like, you open up a whole new world, right? Because you created what we set out to do, this quantum system where everything is mode matched to each other. And so one thing we're able to do, so if you have two emitters that are not only frequency matched, but actually very close to each other, closer than the wavelength separated, then they will act in concert. They will couple to each other and no longer act like two emitters, but like one emitter. So for example, you take a tuning fork and you hit it on a table. There are actually two modes. There's a So I have symmetric mode and anti-symmetric mode in that tuning fork. And the symmetric mode doesn't last very long, right? It quickly radiates power out into the world around it. And then the one that survives is the anti-symmetric mode, right? Because that's more balanced, but it's quieter. But that's actually the one you hear because it lasts longer, right? And so it's the same thing with atoms, right? You take, same thing with these quantum emitters. They're very close and they're resonantly coupled. You just bang them on a table, so to speak. You shine some laser on them, and you'll have two modes. You'll have a symmetric mode and anti-symmetric mode, and those are called the super radiant mode and the subradiant mode. The super radiant mode releases a lot of light really quickly, and the subradiant mode releases a little bit of light and just kind of decays. So you can see it here, like ordinarily it's decay, but if you have two molecules very close to each other and resonant, boom, super radiant light, and then subradiant light, which will go down but last for longer. And so why is this useful? Well, it's useful because this super radiant light is actually two photons at the same time. Remember how we talked at the beginning how if you have two indistinguishable photons, they tend to group together? That's what you get. You get this n equals 2 Fock state, right? So here's the G2 experiment which was demonstrated with two molecules that were resonant to each other. Ordinarily, a molecule has a 0% probability of you getting two photons at the same time. But if you're coupled to each other, you have a even greater probability of detecting two photons at the same time. So you're actually able to create multiple photons at the same time Fock states, right? And then this opens up a whole host of applications. So for example, if you're just regular Personian light, like that which comes out of a laser beam, the shot noise, which is your fundamental limit for how precise we view that light, that goes over 1 over square root n, where n is the number of photons, right? And so that's like the fundamental limit of noise. But if you have this, it's called a Newton state, it doesn't really matter. This is multiple photon Fock states where all the photons are traveling together. The fundamental shot noise limit of that goes as 1 over n. And so if you create quantum light, many-body quantum light, you can actually beat the fundamental shot noise limit of the universe and use fewer photons to do more measurements. So here's an example. I think this is only using a 2n Fock state, but here's just this is the shot noise limit, not very well defined. But then you use quantum light, and then you can actually break past that fundamental limit of light and start to detect things. So this is just one of the many, the multitude of examples of things you can start to do once you have a resonant system. But in conclusion, physicists tend to shy away from these molecular systems. I mean, these things have been around since the 90s, but people don't really want to touch them because, well, it's 58 atoms. That doesn't seem like a simple system. But the beautiful thing about quantum mechanics is that more complexity, as things get more complex, in some cases, they can actually get more simple, right? Because think about it, we're trying to do something perfect, right? We want 100% efficiency, but the material we have is fundamentally imperfect. But for whatever reason, I mean, the very idea of quantum mechanics, right, a well-defined energy spectra, means that, I mean, if you were to like resonantly excite an atom in a classical sense, you'd never be able to get that exact indistinguishability, right? Because you'd always be just the tiniest bit off. But when you're talking in the quantum world, because everything's quantized, everything's discrete, everything like falls into this, just clicks into place, you can actually reach something which is akin to perfection, even if the matter you have is imperfect, right? And that's something we've seen demonstrated with diagrams of sterling. Even though it's a large, ugly molecule, you have excellent quantum properties, it's lifetime limited. You have the superpower, which only comes about because it's such a complicated thing and because you don't understand it, which is that you can shift the resonance just using light. And who knows, probably has plenty of other properties which allows for me fantastic and scalable quantum technologies. So thank you all.